So yesterday we were talking about the subharmonic function and their properties. Still we haven't written the definition of the subharmonic function. So subharmonic function was defined in this way. If omega is any region and v is a function from omega to r. Now define a subregion D of omega and U is a harmonic function defined from D to R and U is continuous on the boundary of the D, and in such it is defined in such a way that V is less than or equals to U, V is less than or equals to U on D, and also V is less than or equals to U on the boundary of D. In that case, we will call that V is a subharmonic function. In that case, we will call that V is a subharmonic function. So, what is the property? Firstly, this V is defined from the superdomain to R, and this U is a Laplacian on the subdomain of this region. Like U is a Laplacian on D, and U is continuous on the boundary of D in such a way that V is less than or equals to U on D as well as on del D. So it basically implies that V is less than or equals to U on the union of D and del D. So that is basically D closure. In that case, because since V is less than or equals to this harmonic function U on this domain D, then we call it a subharmonic function. And then we had to prove some property of the subharmonic function. So we were on the third to fourth, we proved no. Yeah, so we were here. So third property, my voice is echoing. I don't know why. Roberto, can you please mute yourself? So third property was V at P, where P is the center of a disk with radius epsilon d theta. So we have to prove that for every region D contained in omega and for every U harmonic in D satisfying the property V is less than or equals to U, either it will be strictly less than U or it will be equal to U in D. So let's see. Let U is harmonic in D, satisfying V is less than or equals to U, and assume W equals to V minus U. Then W is less than or equals to 0 in omega because V is defined to be less than or equals to U. So V minus U will be less than or equals to 0. So W is defined equals to V minus U. So because of that, W is going to be less than or equals to 0 in this region omega. Assume that W of A equals to 0 for some point A belonging to omega. It is less than or equals to 0. So either it will be strictly less than or equals to 0. But we are assuming that there are some point, say A, we are just assuming the contradiction. We are not saying that it is going to strictly less than u or it is going to strictly. We are assuming that it had some point at which v is equals to u, that is w of a equals to 0, and some points at which v is strictly less than u, like it is a combination of the points for some a belongs to omega. Now we show that in this case we are going to show that when it is vanishing even at a single point in the region omega, then it is going to vanish throughout the omega. So we show that w is equals to 0 in all of omega. Define the set E equals to P belongs to the domain D such that W of P equals to 0. Now, the one thing which we are keeping in mind, we are taking only those points at which W is vanishing, which are coming from the domain D. We are not taking this the whole reason omega, because u is the harmonic function defined on the domain D only. U is, we don't know about u whether it is harmonic on omega or not, but we are very sure that u is harmonic in the region D. So that's why we are picking up those points at which v equals to u, that is w equals to 0, and those points we are choosing from the domain D because U is defined to be harmonic in the domain D. Now according to our assumption, since W of A equals to 0, A belongs to omega, so since U is coming to be from U is defined on D, so there should be some point for sure is clearly non-empty according to our assumption and closed in omega. Now we show that E is also open. The property of closeness is coming from the closeness of D union del of D. Now we show that E is also open. So let epsilon is greater than 0 be as in point 3. So epsilon is defined in such a way that we are forming a ball centered at P and its radius is epsilon 3. Now since U is harmonic in omega, it satisfies the mean value property. So in view of point 3, we have for any radius r such that radius lying between 0 to epsilon, W of P is equals to 0 is equals to Vp minus Up such that it will be less than or equals to 1 over 2 pi 0 to 2 pi. Now V is less than or equals to U and U is a function from D to R such that U is harmonic and U is continuous on the boundary of del D and V is also continuous in the whole region omega. So under this property it is going to be a harmonic, and since it is less than or equals to U, so because of that it is a subharmonic function. So when we are applying the mean value property in the region in the subset of D, because B P comma epsilon is going to be subset of D, so V and U will also be harmonic in this disk, and using the mean value property that is defined for the harmonic function, v p plus r e to the power iota theta minus u p plus r e to the power iota theta d theta, that is equals to 1 over 2 pi 0 to 2 pi w p plus r e to the power iota theta, and according to our assumption d theta that is less than or equals to 0. Since w is less than or equals to 0 in D, clearly w of p plus r e to the power iota theta equals to 0 for all theta and all radius are less than epsilon. So when w equals to 0 in this case, and it will also implies that E is open. Now since capital omega, since the region omega is connected, and this is this sorry this E is an open set in this region, so because of the connectivity of the region omega, E is going to be equals to omega. So W equals to 0 on the whole omega, like V equals to U on the whole omega. Rather than saying V equals to U on whole omega, we can say that V equals to U on D, because we are talking about the harmonicity of U only on the domain D. The next point is the next point was, for every region D contained in omega, it will be either this property holds, so we have to prove this property, the first one. So suppose we have given the property either V is strictly less than U or V is equals to U. Then we have to prove that V is less than or equals to U on D, and V is less than or equals to U on the boundary of D. So suppose the fourth property holds that for every region D contained in omega and for every U harmonic in D satisfying V equals to U, either V is less than U in D or V is equals to U in D. Suppose it holds. Now we have to prove that fourth to one. We have to prove that for every region D contained in omega whose closure is compact and contained in omega, that is D closure, it is a compact set and it is contained in omega, then for every function U continuous on, for all U continuous on, closure of D and harmonic Laplacian of U equals to 0 in D. If V is less than or equals to U on the boundary, then V will be less than or equals to U on D. So we have to prove that we have this information, and we have to prove that this holds. So let's proceed. Let V, comma U and D be as in point 1 and let W is equals to V minus U. Then according to this definition, W will be less than or equals to 0 on the boundary of D. Now let M is defined as the maximum of WP such that P is belonging to D closure. Now since W is continuous on compact state D closure, M is attained on this set if it is attained on the boundary of D, then if it is attained on the boundary of D, then clearly V is less than or equals to U on D. Since V is less than or equals to U on the delta of D, we have defined W is less than or equals to 0 on the delta of D. So if we are assuming that the maximum value is going to attend on the boundary, then if we are assuming that the maximum value M, that is W of P, is going to attend on the boundary, then for all the value which is lying inside the region will for sure less than or equals to M, that is the other values which is lying inside the region D for sure will be less than or equals to M, that is W of P, that is it will be less than or equals to V minus U, because this is the definition. We have assumed that V is less than or equals to U on the boundary of the domain D, compact set D. Otherwise, there is a point P naught belongs to D with W of P naught equals to M, and if we replace U by capital U is equals to U plus M, we see that capital U is harmonic in D, because this is a constant. This is W minus U is going to be a this M is going to be a constant. So U is harmonic in D and V is less than or equals to U in D, and V of P naught is equals to U of P naught for P naught belongs to D. So by point 4, V is equals to U in all of D, hence on the closure of D. Thus, V minus U is equals to M on the boundary of D, and since V is less than or equals to U on the boundary of this, M is will be less than or equals to 0, and which implies V is less than or equals to 0 on the on the D. So this was the proof of this theorem, and I am not going to write the definition because well, let me write. I think you guys are clear with the definition of the subharmonic function. So basically, the subharmonic function is defined from the region omega to R in the case when we are able to find a subdomain of this region omega such that there is a harmonic function from D to R and V is less than or equals to this U on D closure, that is D union boundary of D. So in that case we call V a subharmonic function. So any real valued continuous function u we define on a connected open set omega is said to be subharmonic if it satisfies any one of the four conditions of the above theorem. So we have studied the subharmonic function in this way. Mostly I am explaining in this way that you are able to find a harmonic function from a subdomain of this connected open set such that v is less than or equals to u on the this connected open set. But if even it satisfies any of the three properties, this was the first property. This in the most of the book they are saying that subharmonic function is defined in this way only. But I was able to find a book. There were four definitions of the subharmonic function. So if any of the four condition is satisfied, it is subharmonic. But most of the book mention only this definition, that you are able to find a harmonic function in subdomain of omega such that v is less than or equals to u in this connected set. Just that is the definition of subharmonic function. So maximum principles for subharmonic function. This is theorem, but we are not going to see the proof of this theorem. Maximum principle for subharmonic function. So first we form if v is subharmonic in omega and v is less than or equals to m in omega, then either v will be strictly less than m or v equals to m. So in the fourth condition, we were proving that either v equals less than u in d or v is equals to u in d. So this weak form basically comes from the definition of the fourth point. Either v will be strictly less than m or v will be is equals to this m. So it cannot be globally bounded by a constant. This is a constant. So this definition is saying that if V is globally in this region omega V is globally bounded by a constant, then either it will be strictly less than that constant or it will always be equals to that constant. It is not that at some places is going to be equal to that constant and at some places it is going to be less than. So either it will be strictly less than this constant m or it will be strictly equals to this constant m. Let's talk about the strong form. If omega bar is compact and V is continuous on omega bar and harmonic in omega, then V attains its supremum on the boundary of omega. So in the case we have only two things. Omega is open and omega is connected. So we were defining the weak form. If V is globally bounded by a constant m, then either V will be strictly less than that constant or it will be strictly equals to that constant. In the strong form, we are imposing one more condition that omega bar is compact. Omega bar is compact and V is continuous on this omega bar. So under these two conditions, it is sure that the maximum value of V will be attained on the boundary of the omega. V will attain its supremum of V will belongs to the boundary of omega. So this is the strong form. So for a strong form, omega bar has to be compact and V has to be continuous on omega bar. Even defining the differentiability and continuity on the open set is easier than the defining the continuity on the closed set, even continuity on the closed set. There is a proposition for the subharmonic function. We have sum of two subharmonic function is subharmonic. In particular, the sum of a harmonic function and a subharmonic function is as we saw that the sum of the two harmonic function was going to be harmonic. So in the same way, sum of the two subharmonic function is going to be subharmonic, and if you will be more specific about this summation, then you can say that sum of a harmonic and a subharmonic function is going to be subharmonic. So it will subharmonic, it has a more restriction and harmonic has the less restriction. So when you are going to add these two functions, the more restriction will be imposed. The second point is non-negative multiple of a subharmonic function is we are talking about the non-negative multiple of a subharmonic function. Why it is so? So just keep in your mind how we define the subharmonic function. We say that V is a function from open and connected set omega to R, and U is a harmonic function from the subdomain of omega, and it is harmonic function, and also this U is continuous on the boundary of V such that V is less than or equals to U, then we call V is subharmonic function. So we are taking the non-negative multiple like any lambda of v where lambda is greater than or equals to 0, in that case it will be a subharmonic function, because if you are going to take the negative multiple, suppose you are multiply something negative, so it may violate this condition. So that's why we are taking the non-negative multiple, isn't it? Because we are taking v is less than or equals to u, so v minus u is going to be less than or equals to 0. In case if you are taking a non-negative multiple, so it might be possible that minus lambda minus u might be greater than 0. So it can violate this condition. So that's why we are taking the non-negative multiple of a subharmonic function. So this point, non-negativity, is a very important point to say this statement. Third, maximum of u comma v is subharmonic whenever u and v are subharmonic. This point is very trivial, because if either u or v are subharmonic, then for sure their maximum are going to be a subharmonic function. These two functions u comma v are subharmonic with respect to a single function. Rather than saying u, I would say that w, because every time we have defined a subharmonic function, the harmonic function we have chosen u. So maximum of w comma v is going to be subharmonic whenever either w or v are subharmonic. Okay. So it is, these two are subharmonic with respect to same function. For sure, their maximum, even their minimum, is going to be subharmonic. So can anyone tell me what is the definition of the Riemann surface? Hmm? Do you guys have idea about the Riemann surface?
No.
Okay. Do you have idea about the one-dimensional manifold? Okay, forget about it. We are just going to read the theorem then. Okay, so Riemann surface is defined as a one-dimensional manifold in the complex plane. So basically, if you are saying the one-dimensional manifold in the complex plane, so complex plane is nothing but r cross iota of r, because every number u belonging to C, basically we write u equals to a plus iota beta. A is coming from R and B is coming from R. So when we are saying that a Riemann surface is one-dimensional manifold, so one-dimensional manifold in the set of the complex number in the plane of a complex number, then it will be a two-dimensional manifold in the set of real number, in the space of real number, because basically how we treat complex space or complex plane is a two-dimensional real space. And how this two-dimensional space is taken, it is taken in this way: r cross iota of r. So the Riemann surface is defined as one-dimensional manifold, but in the complex plane, in the complex space, when you will be talking about the Riemann surface in real space, then it is a two-dimensional manifold. So let capital X be a Riemann surface. So this capital X is one-dimensional manifold in C. And omega a connected open subset of capital X, a continuous real valued function V on omega is said to be subharmonic if for every coordinate chart U to Z. What is the meaning of coordinate chart in the Riemann surface? So Z is a function and U is a open set in this Riemann surface. So this coordinate chart is defined as, say, from U to Z of U. So basically, we consider those points under this mapping which has a pre-image. We consider those points like this is the coordinate chart, so it is defined from U. Suppose it is defined to another set V, then we say that J of U is equals to V. What does it mean? If I am saying that Z of U equals to V, then what does it mean in a sentence way? What do you call it? Hmm? If I say that each of the point of V has a pre-image in U, then what you call it? What kind of function they are? If each point of V has a pre-image, then pre-image under the function Z, then what we call this function? Please tell me. If the codomain has a pre-image for each of its point, then what kind of function we call? Okay, suppose that if you are defining a function from A to B such that f of A1, f of A is unique for all A belongs to capital A, then what do you call it? We call it a one-one function, this one, if it is taking a unique value for each of Sorry, not this is not the thing. So it is defined in this way. F(a1) is equals to F(a2), then A1 is equals to A2. So this is one function, and we call that if the codomain has a pre-image for each of its value, don't we call it onto function? Isn't it? This is an onto function.
Yeah,
Do you guys have idea about the basic definition of one function, onto function, homeomorphism? What is a homeomorphism?
it's a continuous function with inverse continuous, I think.
Yeah, so when you are defining inverse, for that you have to be onto function and one function. In that case, inverse will exist, isn't it?
Hmm.
I think this theorem is going to just pass your here, and then it will cross your head because it is using a lot of property of onto function, homeomorphic function, and I don't think you guys remember anything. So for every coordinate chart u comma z, this coordinate chart is defined in such a way that it is defined on a open set u of the domain omega. You can say that x, this u is a subset of x such that this z is an onto function, like z is defined from u to z of u. So this function is for sure onto. So with this set is contained in omega. Now V of Z inverse is subharmonic in Z of U. So when we were not talking about the Riemann surface, we were simply taking an open set omega and we were defining a function b that is a continuous function from this open set omega to r such that v is less than or equals to u for a harmonic function which is defined from d to r and u is continuous on the boundary of d, then we call it a subharmonic function. Is this definition clear?
Yeah.
So now when we are defining the subharmonic functions on a Riemann surface, like in a one-dimensional manifold in the complex plane, then we are not applying this condition. We are not applying this condition. We are saying that you have to find out that for every coordinate chart u comma z, the operation J inverse is subharmonic in z of u. So the definition has changed a little bit, but not like totally. Let us call a coordinate chart u comma z. Every time when I am talking about a coordinate chart in a Riemann surface, then just keep in your mind that if x is a Riemann surface and I am saying it a coordinate chart, then z, this u have to be open. U is open subset of this x and z is defined from u to z of u, because in the coordinate chart the function is assumed to be an onto function. The function is assumed to be an onto function. Coordinate chart u comma z, a parametric disk with center P belongs to u and radius r if z of u is a disk in the complex plane with center Z of P and radius R. So let U comma Z be a parametric disk with center P and radius R with closure of U lying in omega, then by mean value of V on the boundary of U denoted by this mean value is denoted by M V comma U V mean. This is like V is V implies because mean and it has been used a lot of time. Over 2 pi integration 0 to 2 pi V operation Z inverse Z of P plus R e to the power P dt. Just take a look at this definition and just give me 2 minutes. I will be back. Just read this definition and try to understand. I will again explain it and then we'll come to a theorem. Just give me 2 minutes.
Okay.
So how we define, just take a look. We are taking x. This is a Riemann surface. So this is a one-dimensional manifold in C, or you can say that it is a two-dimensional manifold in R of 2 because this C can be written as R cross iota of R. And then we are taking omega, that is a subset of capital X, and it is an open and connected subset of capital X. And we are defining this function V from omega. It is going to C. Is said to be a subharmonic if for every chart, like any chart, coordinate chart, you are taking U Z, like Z mapping from the open set to Z of U. So, or you can say Z is mapping from U to another open set V such that Z of U equals to V. Both are the same statement, whatever you want to say. So basically in this coordinate chart, the way to define this coordinate chart is that this Z function is defined on the open subset of the domain, open subset of this connected set A. So U is subset of a connected set omega, and this is a open subset of omega. So Z is defined on the open subset of the connected set omega such that it is an onto function. Z is an onto function. Then V of Z inverse is subharmonic in Z of U. Now, if we are taking U comma Z is a parametric disk and we are taking P a center of U, P is belonging to U and it is a center of U and radius R if Z of U is a disk in the complex plane with center Z of P and radius R, then using the mean value property this holds. So this is very complicated and very complex things to understand. Even I get confused sometimes, so don't worry about that. Now let's write the theorem. Let omega be a connected open set of a Riemann surface capital X and let be less from omega to R be a continuous function, then the following statements are equivalent. The first, for every region D contained in omega and whose closure is compact and unbounded, compact and contained in omega and contained in omega and for every function U continuous on D bar and harmonic in D if V is less than or equals to U on the boundary of D, then V is less than or equals to U on D and hence also on D bar. This is the very first statement of the theorem which we have proved in the last theorem where we have to prove that 4 points were equivalent. So in that theorem the only difference was that omega was a connected open set in C. We were not talking about this Riemann surface. However, in this theorem, the only difference from the previous theorem is that omega is a connected open set of the Riemann surface capital X. So, only difference is that, and everything is same. So, every time when you are like, if you want to prove, I know you are not going to prove, but still, if you want to prove, then you have to define a subharmonic chart, and then with this subharmonic chart you can say that V of Z inverse is going to be a subharmonic function defined on this subharmonic chart, and then you have to prove this theorem for this, and then you have to extract it for V. And second, for every point P belongs to omega and for every parametric disk U comma Z with center P, radius R, and whose closure is contained in omega. We have V of P is not equals to M V comma U. We already have defined the value of M V comma U. This is given by, this is the mean value. So for the time being, I am just leaving the Perron's method. Like, you may read that theorem. I have already uploaded the notes. I am not going to prove it because it is making more theorem based, and you guys might be confused. So just read that theorem. If you are not getting that theorem, then we can discuss it tomorrow. And for the time being, I would like to talk about the heat equation. So can anyone tell me the equation which represents the heat equation?
Sorry, can you repeat the question, please?
What is the equation of the heat equation?
U of T equals to a constant by the secondary of UXX can be, or
So you can
the
say,
Laplacian, yeah.
yeah, Laplacian of u, because so if we are talking that the heat equation is on the steady state, so what will be the equation of heat? If you are talking on the steady state, then what will be the equation of heat?
The Laplace equation.
Yeah, so the steady state case means it does not change with time t. It does not change with time t. Suppose you take a rod, suppose you take, I'm just trying to plot a figure because we have gone through a lot of theorem and it has been like, I can feel you. So suppose you are taking a rod and after some time you start to heat this rod at this point. You start to give heat at this point and heat starts to flow. Heat starts to flow in this rod. And suppose after some time T of C or saturation time, say saturation time, after some time T equals to T of S, the heat of this rod is uniform. The heat of this rod is uniform. Then what will happen after this saturation time? Even you are giving more heat, is it going to affect this rod? Suppose this is the saturation time and at after like at this saturation time the heat of this rod is uniform, like at each point it has same heat. So if you are heating it more, then is it going to increase the heat of the rod? Just think and tell me, what do you feel? Suppose you take a rod and you start to heat at this point, and I am saying that after the time t of s, the heat of the rod, the temperature of the rod is uniform. The temperature of the rod is uniform at time t equals to t of s. Then if you give more heat at this point, so whether it will increase the temperature or not.
Yeah, I think.
How? For me it is not going to increase Because if I am saying that it has a temperature of the rod has been uniform, so for sure it acquire its maximum heat at this point, then it pass heat to the another point, then again it acquire its maximum heat, then it pass to, like firstly it acquire minimum and minimum and minimum, but when the temperature of the rod is uniform, then for sure all the cross section of the rod is going to be at the its highest heat, isn't it?
Yeah.
So it means we can say that now even if you are this rod, it is not going to, if this U is temperature, if this U is temperature, so after this saturation time, the heat of the rod, the temperature of the rod is constant, that it is not varying with the time. So steady state has arrived. In that case, this heat equation reduced to this equation, that the Laplacian equation, and we know a lot of property of the Laplacian equation, isn't it? We know that this solution of this Laplacian equation is a harmonic function, and even we know its fundamental solution in the form of the Poisson kernel. Do you still remember what is the Poisson kernel, or you guys have forgotten about that? Do you remember about the Poisson kernel and Poisson integral formula?
I don't remember exactly the formula, but I remember.
Idea, just idea. I'm not talking about the exact formula. Do you guys have idea what is this Poisson kernel?
Yeah.
Yeah, only idea. I even I don't remember exactly, but you should have idea that we for this Laplacian of u, if it was in two dimension, if it was in two dimension, then what we did, we write the solution of this as a variation of separation of variable, and then we got a solution that was the summation of n varying from something and summation of something. Then this was a series solution. This was a series solution. So to write a closed form solution, we did some kind of trigonometric arrangement, and in that case, we could write the solution of this Laplacian equation on a circle or on a disk or on a sphere in the integral form, because in the interior of a circle, we assume that r is going to be less than or equals to 1, so the series was convergent, and in the exterior of the circle, r is going to be greater than or equals to 1, but 1 over r is going to be less than. So using this property, we say that this series was going to be converged, and in that case, we could write the summation of the series is like, if it was like r to the power n, so it was 1 minus 1 over r over 1 minus r, when this r was less than 1. So using this property, we could write this summation as a converging value, and in that case, we could write the closed form solution of a Laplacian. So just I would request you just take a quick look on the previous topic. The next topic, heat equation, is going to be really easy if you already know the Laplacian equation. If you already know the Laplacian equation, then the heat equation is going to be very easy. So tomorrow, can anyone remind me which topic we have covered in Laplacian equation? Do you guys remember? Let me write. In the Laplacian, we have studied the derivation of the Laplace equation, from where it arises. So basically, it arises when electric charge is coming from infinity to a point. So Laplacian equation, we have write the derivation of that. We have write the derivation of the Poisson equation, and then we saw that the solution of the Laplacian equation is going to be harmonic function, and then we proved a number of theorems based on this harmonic function. That was really super easy. Like we studied the mean value property, it was really very easy. And using this mean value property, we study the maximum minimum principle. These are very important topic for your general exams, maximum minimum principle, and then we study the Green's function, we study Wisk's Poisson, kernel, and Poisson formula, and then we study the energy method, and then we study the eigenvalue problem, and then the last was subharmonic. And Perun, I have left it to you. So I would like to ask you if you forgot about these two topics because you have covered these two topics in the last 2 days. Do you was these topics were clear to you, all of you, or not? Not super clear, but still it was clear and easy to all of you or not, these topics.
Some topics are clear for me at this moment, I think.
Yeah, so which topic is not very clear? Like we can revise it. Which topic is not very clear? Would you please mm, point out? Laplace is clear, derivation of Laplace and
Yeah.
harmonic function,
Yeah.
mean value property.
I need to study that, but yeah.
Please read the mean value property. I think it is easy, but if you don't get it, then please ask me tomorrow in the beginning of the class.
Okay.
Maximum minimum principle. I
Yeah.
think mean value, if you have mean value property, then it was really very easy. Poisson kernel.
Yeah.
Green's function was tricky because it is basically the theory, so that's why it might be tricky. But you are already aware of the Green's function in your engineering topics and for most of the undergraduate course. Energy method,
I need to read.
eigenvalue problem.
Yeah, it's clear that.
Okay, so energy method is somehow related to the calculus of variation. So because if I am going to explain it a lot, so it could take a lot of time and we have to still cover to 2 units. So that's why I was not giving a calculus of variation. Roberto, you want to ask something? Okay, so please read this topic. If you are unable to get the mean value property, then please do ask. We can go over that again. Energy method, I won't say that it will be very clear to all of you because somehow it is, I am using, like you can see that I am just writing the variational principle. Now I cannot derive the variational principle for you because I need to remind you all the calculus of variation. So because of that, I won't say that, but the mean value property is really very easy for me. Subharmonic function, the definition was easy, but the theorem was little bit difficult, and I feel that, so that's why I'm not going to talk about that. But if in these topics you are understanding at least half of them, then still you are on a good point. Next, we are going to talk about the derivation of the heat equation, like physical interpretation of the heat equation. I have already uploaded the notes. So if you want to go over that, please go over that tomorrow notes. And you don't need to worry about the heat equation. In my point of view, it is really easy. Why? What happened? Everything is fine. Okay, so if you guys have any doubt, then you can ask another. We can start the heat equation tomorrow, and by tomorrow we will finish the fundamental solution of the heat equation because it is really. I think that the heat equation is going to be very easy because you already know the mean value property, the weak maximum, minimum principle. So, yeah. Okay, so see you. Yeah, see you. Bye. Bye.
Bye.